All right, now we're going to look at a different definition, which is a Bronsted-Lowry acid. And this one's a little bit more inclusive. It includes things that wouldn't normally be classified. So a Bronsted-Lowry acid is a substance that donates H+. And you'll often see this labeled as a proton because H plus is hydrogen, and hydrogen has a proton and an electron, but H plus is literally just a proton, H plus in a reaction. So that is a Bronsted-Lowry acid, and a lot of times it doesn't change a whole lot. So for example, HCl is an Arrhenius acid because it's split apart, but if you have HCl reacting with water, what you can say is that HCl donates an H plus to water, and if it does that, it becomes Cl minus, and then water becomes H3O plus. If you remember, I said H3O plus is pretty much like H plus. This effectively does the same thing as an Arrhenius acid, but that makes this HCl a Bronsted-Lowry acid. I should have written that up here. Now, a Bronsted-Lowry base, same deal. It is a substance that receives an H plus in solution. So if water is receiving the H plus, this is actually a base right here, whereas HCl was the acid. Now, if this reaction ran in reverse, if Cl minus turned back into HCl, what must have happened? It must have grabbed an H plus. So that makes Cl minus actually a base, and it took its H plus back from H3O plus, which makes that an acid under this definition. So for Bronsted-Lowry reactions, you're always going to have an acid and base on one side of the reaction and an acid and base on the other side, and they'll pair up. HCl pairs up with Cl minus. This is an acid and its conjugate base. H2O is a base, and its conjugate acid is H3O plus. So that's sort of an idea here. Now you might be saying, why all these definitions? Well, because there are some bases, for example NH3, which does not fit the Arrhenius definition of a base. It is a base, but this cannot possibly break apart to make OH minus. Instead, what it does is it reacts with water, and it acts as a base. It pulls an H plus off the water to become NH4 plus, and if water loses an H plus, it ends up becoming OH minus, and so it effectively increases the OH minus in a solution, but it doesn't do it by dissociating. So again, NH3 is a Bronsted-Lowry base, but it is not an Arrhenius base. So again, this definition is a little bit more inclusive, and then NH4 plus is an acid, OH minus is a base. There's a third definition which is even more inclusive, known as Lewis acids and Lewis bases, which we're not going to get into this year, but just know that there are many definitions, and each one usually kind of broadens the definition and encompasses a few bit more substances that weren't included in the others. So anyway, that's it. Until next time, I am Derek Genova. Have a delightful day.